As we discussed in the beginning of the class, there are several different levels of computer organization. We began with the gate and transistor level and followed this by the circuit level. We then use circuit components such as the multiplexer to build even more complicated subsystems. We're still interested in the hardware level, of course, but here we're going to use abstraction to hide a lot of the details and look at the overall computer system, that is, its architecture. The von Neumann architecture is the most well-known architecture and is the foundation for nearly all modern computer systems. The von Neumann architecture was first to feature a stored program concept, and the architecture had sequential execution of instructions. There are, of course, non-von Neumann architectures, but they're beyond the scope of this course. There are four major components in the von Neumann architecture: memory, which is a functional unit where data is stored and retrieved; input and output, which connects the processor to the outside world; the arithmetic logic unit, which contains circuits for arithmetic, comparison, and logic; and the control unit, which fetches instructions from memory, decodes them, and executes them. While it's actually a bit more complicated than this, we can divide memory into random access memory, or RAM, and read-only memory, or ROM. Random access memory, or RAM, can be thought of as an array of cells, each with an address. This cell is the minimum unit of access, and access time is address independent. Read-only memory is a section of RAM set aside for system software. We cannot write to the ROM. An important property of memory is the cell width, or how much is stored in a single cell. This is generally 8 bits, which is called a byte. We may need multiple cells to store large numbers or long program instructions. In memory, the address of the cell may be different than the contents of the cell. For example, address 42 might store the content of 10010011. When we get to instructions, they frequently use the address. If we have n bits for an address, we can have a memory of size 2 to the n. This is called our address space. Registers are special storage cells. In the execution of programs, we typically have memory address registers which hold the cell address. The address register should hold as many bits as there are in an address. There are also memory data registers that hold data values. These will obviously be some multiple of the memory cell width. Since W is usually 8, the memory data register could be of size 32, 64, etc., since values are typically larger than 1 byte. Fetch and store are two basic memory operations. Fetch loads an address into the memory address register, decodes the address, copies the contents of the cell into the memory data register. Fetch is a non-destructive operation. Store needs an address and a value. We load the address into the memory address register, load the value into the memory data register, decode the address, and store the contents of the memory data register at the memory address. This is a destructive operation since it gets rid of whatever was previously there. Input-output can be human-machine interface such as keyboard, screen, or printer. It can also be the machine-to-machine interface such as a hard disk. With human-to-machine I/O, we obviously need some encoding and decoding, but machine-to-machine is typically binary-to-binary. Input-output is the most non-standard subsystem, and input-output operations are slow compared to other computer operations, so we often have a separate processor called an I/O controller to handle these operations. The arithmetic logic unit, or ALU, is the brains behind the operation. It has separate high-speed access registers for storage of operands. ALU operations are add, subtract, multiply, divide, and compare. We have circuits for each operation, so all the operations get done. We then select the result we want using our friend the multiplexer. If the ALU is the brains, then the control unit is the manager. It tells the other subsystems when to do their thing. The control unit contains a program counter, or PC register, that holds the address of the next instruction. There is also an instruction register, or IR, which holds the encoding of the current instruction. Finally, there's an instruction decoder unit, which decodes the opcode of the instruction and signals helper circuits, one per instruction. Here is a larger view of the von Neumann architecture with all its subcomponents. This is taken from U.H. Hilo's very own Judy Gerstein's text called Invitation to Computer Science. If you want a great overview of our field, I highly recommend this text. But here you can see the overview of the von Neumann architecture and the different things that are involved with each of the four components. So far, we have all the working components of an idealized machine, but how does the control unit actually run a program? It does this through a cycle known as fetch, decode, and execute. In the fetch phase, we get the next instruction into memory. The decode phase is where the instruction decoder gets the opcode, and the execute phase is different for each instruction, but executes the instruction. The fetch phase is a bit more detailed than let on. We start by seeing where we're at in the program counter, and sending this address to the memory address register. We then initiate the fetch and send the data from the address to the memory data register. The instruction then gets moved to the instruction register. Lastly, we increment the program counter by 1 to go to the next instruction. Now, decode actually involves decoding the operation in the instruction register, and for this we use our old friend the decoder. Execute depends on the operation involved. Our operations are given by an instruction set associated with the machine. In this figure, we can see an example instruction set with 16 different instructions. Let's look at how these work, and we'll begin with load. Load X means moving the contents of address X to register R. We start by sending the address in the instruction register to the memory address register. We then fetch the data from this address and move it to the memory data register. Finally, we move the data in the memory data register to the register R. Store X means moving the contents of the register to memory location X. We start by sending the address X to the memory address register. Next, we send the data in the register to the memory data register. And finally, we store the contents of the memory data register in location X. Addition is a bit more complicated. It means we're adding the contents of location X to the value in the register. We start by sending the address X to the memory address register. Next, we initiate the fetch and move the data to the memory data register. We then send the data in the memory data register and the data in the register to the ALU. We select the add circuit as the result and copy the result into the register. Jump means to get the next instruction from location X. We need to send the address from the instruction register to the program counter and then fetch it. This instruction is useful for loops, subroutines, and even for conditional statements. We can also do comparisons with the compareX command, which compares the contents of address X with what is in the register. We use the result to set the condition code registers of greater than, less than, and equal to. This is useful for conditional statements and for controlling entry into loops when combined with jumps. Imagine that we have a 4-bit opcode and a 12-bit address. This is what a typical program listing might look like. Can you tell what it does by looking at it? I'll wait a bit. The way to figure out is to take each command and translate the opcode, or the first 4 digits, using the table we had earlier. We also need to translate the address to a number. This is done line by line. The reverse process applies when writing a program. We write out the algorithm using the instruction set and carefully locate the data in the appropriate addresses in order to allow the program to run. We then translate the program into binary for execution on the machine. Yikes. In the words of the students that did this lab, this kid cried as a result. This is what early programmers faced, but there was an easier way to go about things, and we'll cover that in the next episode. Thanks so much as always.